Shown in the figure below is a mass analyzer system. This system operates by accelerating a charged particle across the gap between two capacitor plates, giving it energy. After the particle has been accelerated, it enters a magnetic field and is bent in a circular trajectory until it reaches the exit. You are to design the mass analyzer system so that the carbon-12 ions, whose charge is 1.6 times 10 to the minus 19 coulombs, and whose mass is 12 times the proton mass, or 2 10 to the minus 26 kilograms, and these are accelerated to an energy of 25 MeV. This is a lengthy problem, but not at all a difficult one. We can imagine in our mind that the problem is divided into two pieces. The portion to the left of the dashed green line is an energy problem, and the portion to the right of the dashed green line is a force problem using magnetic force. We're going to begin our analysis by analyzing the energy part of the problem, and as with all energy problems, the technique by which we solve it is to identify two moments. We will label these as moment 1 and moment 2, and we'll connect moment 1 to moment 2 using the principle of conservation of energy. In first semester physics, we know of 4 forms of energy, and in second semester physics, including electric potential energy, we know of 5. So we ask ourselves at moment 1, is there kinetic energy, rotational kinetic energy, gravity, and spring? None of these exist at moment 1. However, at moment 1, we can see that there is an electric potential energy, and the amount of potential energy is charge times voltage, and we'll give this a V1 for the voltage experienced when the particle is at location 1 at moment 1. At moment 2, we certainly do have translational kinetic energy. In fact, we have 25 MeV worth of translational kinetic energy. However, we have no rotation, spring, or gravity, but we will have an electric potential energy equal to the charge of the object times the voltage at location 2. Bringing all the voltage terms to the left-hand side of the equation, we'll see that Q times the difference in voltage is equal to 25 MeV. This problem currently contains a mixture of units. Since MeV is on the right-hand side of the equation, meaning that charge would be quantified in e's, whereas the charge given in the problem is in coulombs. If you'll notice, the charge of this ion is actually 1e. Therefore, we can see in choosing between coulomb as our unit of charge and e's as our unit of charge, we will certainly have a simpler problem if we put 1e for the charge on the left-hand side of the equation, and then have an extremely simple cancellation of the e's left and right to tell us that the potential difference across the plates is 25 million volts. And this is the answer to part A of the problem. For parts B and C, we'll be analyzing the voltage and electric field of a capacitor, and we'll take a moment to review those calculations before we proceed. A parallel plate capacitor is what you get when you take two plates of metal and face them towards one another. If one of these plates becomes positively charged, the electrons in the other plate will rearrange in whatever pattern is necessary to ensure that no electric field lines enter the second conductor. Clearly, the amount of charge required on the right is equal and opposite to the charge contained on the left, and therefore we can consider a capacitor as having a plus Q to the left and a minus Q to the right, and we will refer to a capacitor in this condition as having a charge Q. In this configuration, every field line that begins at a positive charge ends at a negative charge, and this is how no electric field lines entered into the conductor. There is one small caveat. If we were to look at the very end point of the capacitor, it isn't really true that the electric field lines will go straight from left to right. In fact, the electric field lines are going to sort of bulge at the end. We are going to make an approximation that says that the electric field lines don't do that. Instead, we will assume that the electric field lines at the end are very similar to what they were in the middle, simply uniform going from left to right. This approximation is of course not exactly true, but it is true whenever the length of either side of the capacitor plate itself is much, much larger than the distance d that separates the two plates. Once we've accepted this approximation, we then find that the parallel plate capacitor is the easiest Gauss law problem that exists in nature. Let's begin with our solution, and as always, we will draw a Gaussian surface so as to be perpendicular to the electric field lines. Obviously, the electric field is going to drop off at the ends, and we require the Gaussian surface to be closed, and we will close the Gaussian surface in the manner shown in this figure. In this case, our Gaussian surface is faceted and can be recognized as having end cap 2 on the right, end cap 1 on the left, and sides surrounding it. Therefore, our Gaussian integral of the flux leaving our closed surface will be composed of multiple terms. These terms are the two end caps plus the sides. Fortunately, there is no electric field located at end cap 1, so there is no flux there. And furthermore, along the sides, the electric field does not poke the Gaussian surface, but rather runs along it, again resulting in no net flux. So that the left-hand side of our Gauss law is simply going to be the electric field times the area of end cap 2. As always in Gauss law, this is equal to the charge inside the closed Gaussian surface divided by epsilon naught, and our Gaussian solution will result from finding the appropriate substitution both for the area and for Q in. The reason we refer to this as the easiest Gauss law problem that exists anywhere is that the area is simply A, and that the Q in is Q, yielding the final result that the electric field is Q over area times epsilon naught. Although this formula is complete and correct, we're also going to want to consider voltages. And we know that there is a relation between electric field and voltage, where a difference in voltage is an integral of an electric field, and conversely an electric field is a derivative of voltage. Two small items make these from appearing other than a simple derivative and integral. The first is that since the electric field points downhill in voltage, there is a minus sign in each equation. And second, because electric field is a vector and voltage is a scalar, we need to appropriately account for that with a dot product in the integral formula and partial derivatives along each direction in the derivative formula. In our simple case, we have found that the electric field is a constant, meaning that it will come out of this integral so that the voltage will simply be the electric field times distance, giving us a second relation in our derivation, that V is QD over epsilon naught area. Finally, capacitance is defined as charge per unit voltage, and therefore we can simply solve the previous relationship to have the result epsilon naught area over D for the capacitance of a parallel plate capacitor. All three of these formulas will be necessary to solve parts B and C of the preceding problem. In part B, we are asked to find the electric field between the plates using the fact that the distance between them will be 1 meter. In our previous derivation of formulas, we found that electric field is the voltage divided by the distance d, and therefore we will have 25 million volts divided by 1 meter, which is 25 million volt per meter. In part C of the problem, we're given the information that the area of the capacitor plate is 50 square meters and asked to find values for both the capacitance and the charge on this device. The capacitance we can form geometrically as epsilon naught area over d, using the area of 50 square meters and a distance of 1 meter. When we plug in the values, we get a result of 4.43 times 10 to the minus 10 farads. Please note that the capacitance of the pair of plates depends only upon geometric information such as area and distance, and does not change as you charge up or charge down the plates. This is simply a constant. Finally, we need to calculate the charge, and we can do that using either the potential or the electric field. The charge on a capacitor is always equal to the voltage times the capacitance, or if you prefer, you could use field times distance times capacitance. It doesn't matter which one of these you use, you will get the same result of 0.011 coulombs. This ends the analysis of the accelerator part of this problem, and now we're going to go on and solve for what happens in the magnetic field. Because magnetic force is a velocity-dependent force, the first thing we're going to ask is what is the velocity of the ions after they accelerated by the capacitor. We recognize immediately that the information we're given is the kinetic energy of the ions after they exit the capacitor, and that value is 25 MeV. Once again, we see we have a mixture of units. Joules are coulombs times volts, But an alternative energy scale is to take the charge of the electron times volts. Here we have a mixture in that the mass was given in kilograms and the energy was given in EVs. This time the problem will be easiest to approach by converting everything to MKS, in which case we need to eliminate the E and replace it with coulombs. To do this, we see that we can rig E in the denominator and coulombs in the numerator of our unit conversion, and we recognize that each single electron, or one electron, is 1.6 times 10 to the minus 19 coulombs. This gives us the desired cancellation of the two E's, and therefore, remembering that the M in MeV is 10 to the 6th, we're going to come up with an energy of 4 times 10 to the minus 12 joules. Solving the previous equation for velocity, we find that the velocity is square root of twice the kinetic energy over the mass, and using the mass value that was given in the problem originally, we get a velocity of about 2 times 10 to the 7 meter per second. Although this velocity would be exceptionally large for a car, it is not actually that high of a velocity for a single charged particle. Typically separating high velocities from low velocities is the value of a tenth of the speed of light, which would be 3 10 to the minus 7. Since this is below 3 10 to the minus 7, we're going to consider this to be a fairly slow particle, and this is why we can use the kinetic energy formula 1/2 mv squared without having to access Einstein's more accurate formula for a relativistic particle. To perform the calculation of part E, where we have uniform circular motion, we recognize that uniform circular motion, as always, is a force problem. And the first step in every force problem is to draw a free body diagram. I'm going to take the moment when the carbon nucleus is located there. We find that there is one and only one force applied to this nucleus, and that is a magnetic force whose strength is charge velocity times magnetic field. This is a one-dimensional free body diagram, and so we will orient our coordinate system as shown. And we recognize that this coordinate system, like all good coordinate systems, is oriented so that it points in the positive direction with the acceleration, and that direction is known in centripetal in a circular motion problem. The only force in the centripetal direction is QVB. And then we ask ourselves the question that has the same answer every time we ask it: is there an acceleration in the centripetal direction? The answer is yes. The acceleration in the centripetal direction is v squared over r. Thus we are able to solve for the strength of magnetic field necessary to create this motion. After canceling one of the two factors of velocity, we'll have mv over qr. This is why it is often said that a magnetic spectrometer is a momentum selection device. Plugging in the values at hand, we get a result of 2.09 Tesla. Finally, in the last part of the problem, we are asked to do something rather clever. We're asked to apply an electric field such that the ions would travel in a straight line rather than a curved path. Well, as we recognize, in order for an object to travel in a straight line, we can do so by having a net force of 0. In order to have a net force of 0, we can simply select an electric field so that the electric force of QE is of equal strength but opposite direction to the magnetic force of QVB. In this case, the net force on our particle would be 0, and with the net force of 0, that's when the particle would travel in a straight line. Plugging in the numbers, we find that this will require an electric field of 41.7 times 10 to the 6th volts per meter. And that ends our analysis of a mass spectrometer.